Hello, everyone, and thank you so much for joining today's the second session in the AIA California's Fire Response Series, Home Hardening Techniques, Fire Resistant and Cost Effective. As you get settled, please feel free to say hello and where you're joining from in the chat today. To qualify for continuing education credit, AIA California provides the learning objectives for every webinar and includes them in the PDF presentation that can be made available online. A few quick housekeeping reminders. Today's session is being recorded and qualifies for 1.5 AIA HSW learning units. For those who stay on and watch live, AIA California staff will report these units for you to AIA and will send you follow-up information on how you can receive a certificate of completion. We plan to have opportunities today to take questions from attendees and to the presenters, so please stick around for that. And please be constructive in your comments and questions to help foster a positive learning experience for everyone. I want to say a really big thank you to all the speakers and all those that were involved in organizing today's session. I will be dropping a link in the chat from AIA Los Angeles's website for the event today to where folks can find additional information on our speakers. And I will now hand it over to our first. Thank you so much. Frank?
Good afternoon. Thank you, Sarah. And thank you all for joining us today. Switch over and get my screen up. All right. I'm going to start off our session today, kind of a big picture look on some of the primary drivers about how we actually lose structures in these WUI conflagrations. So our focus is going to be on really fast fires, what I call the 3 risks, and some structural hardening. The first thing, before I get into the details here, is that there's some perceptions that are long-standing in this space, but are not actually correct, especially as we really start digging into the science and the history. One of the first ones is that we think that we have thought for a long time that these WUI conflagrations are actually the result of a massive flaming fire front, kind of a crown fire, sea of combustion coming into the community and rolling over it and burning it. And in the aftermath, that may be what it looks like, but it's actually not high intensity forest fires that cause the most destructive fires. We lose the structures primarily from embers initially that do come from the wildfire. But once those embers start multiple ignitions in the community and overwhelm the initial response that's really designed for interior structure firefighting, once that happens and you start propagating then embers from structures, that propagation is all about conflagration, very little to do with the vegetation at that point. The next presenter is going to start with a slide that really makes this visible. If you look at it, you'll see all the burned out structures, but what you're going to see is a whole bunch of green surviving vegetation in the background. And it's just an indication that once you get into the urban conflagration, it's not a wildfire anymore. Those burned out vegetative pieces are usually from the home's heat rather than themselves burning. So what I've got here are some excerpts from an excellent paper. I've got the citation at the bottom for you to look at. But essentially I just pulled a few key pieces out, but it's really about speed. When you look at this data set, this goes back almost 20 years, and looks at the comprehensive loss of structures in WUI fires, we realize that the highest correlation to that is speed. Essentially fires that go more than about 4,000 acres a day, that corresponds to a large loss of structures. In fact, we can attribute 89% of the structure loss to just 2.7% of the fires. And those are, that's a strong correlation that gets you into this upper 97th percentile of all those incidents. And so we really need to understand that it's really a small percentage of the fires, the very extreme ones where we have these incidents. And the speed is wind driven, and the wind is what drives these embers in. And so we really have to rethink when we're talking about hardening structures, what we're hardening against. And it's primarily embers. It is also lower intensity ground fuels. It very rarely is losses directly to radiant heat, which is kind of what we think of. So in general, you're looking at high sustained winds, low relative humidity. Doesn't necessarily have to be hot. I think the Marshall Fire in Colorado, some of the temperatures were, in the low 50s or 40s. Been on a lot of fires in the middle of the winter that were very cold. We lost a lot of structures because the wind was really what pulled that in. So it's usually going to be close to a community, short term for response. And then it usually is following a period of desiccation or drought. I like to say that we're solving for three risks, and we don't always realize that. We're looking at the same physical space of land and specifically structures. And we want to remember risk, very simplified, is the hazard. In this case, we're looking at fire. So probability of fire, probability of ignition, and then consequence if we do have that. But the three risks really, I've just been talking to you about ignition resistance. How do we actually keep the building from physically burning down? That in itself is an entire focus of risk management. A lot of what you do has to do with regulatory compliance. So you're solving for the risk where one is you're trying to manage the hazard and consequence of ignition, but it's also very real that we're dealing with the hazard and consequence of not being in compliance. We can't just step past regulatory requirements in how we build structures at different stages, and I'll discuss that next. And being code compliant doesn't necessarily mean you're ember resistant. Codes tend to lag behind the field experience, and so you can be code compliant and actually that may not be sufficient for actually having the structure survive from ember assault. And then the third risk is financial risk transfer. This is the realm of insurance, reinsurance, general obligation municipal bonds are starting to get affected because you service those on the property tax off of properties that are increasingly underinsured or uninsurable. And so as you're working through your efforts, realize that we have to solve for all three of these risks, and they are not the same thing. In some cases, they're even conflicted. And so this is one of the areas that this whole issue is in transition from how we used to look at it to where we're going to have to look at it now. And we don't have the systems in place yet that really align these. And so there's no elegant way forward. We're learning this stuff in real time. But just remember, you're having to solve all three of these risks at the same time, and they're not the same, and they may, in some cases, actually be conflicted. So let's talk about the what and the when. Structural hardening, again, to remind everybody, it's primarily about making those structures ember resistant. We do not want to give a place for they individually, they look small and rather harmless. You could probably put most of them out between your fingers. Then you have other larger pieces that are different, but generally it's the smaller ones that can get driven into small crevices where then they can kind of incubate. And you've got a lot of wind. It's almost like a bellows in there. And as these accumulate in these small spaces, you start to generate heat that will propagate out from there. So the first sort of branch of structural hardening is, for what reason are we doing this hardening? And I'll just walk these through the three risks, right? If you're doing regulatory compliance, the hardening might be, there's elements under Chapter 7A that are very clearly aimed, towards that effort. Other states, you may have building codes that aren't as strict in that area. But even in California, we have buildings that are 7A compliant that burn down from ember assault. So there's the regulatory side of how you harden the structure. You can, you refer to those code sets and best practices. And that will solve that portion of it. If you're talking about the risk transfer side, now you're not really making the case about what you're doing to the regulators. they're having to make that case to the people that are accepting the transference of that risk. I got started in this space, I don't know, probably 6 or so years ago, as a fire chief, where I had some property owners who had passed our fire service defensible space inspection. And so we're looking at it really from the structural ignition standpoint. And they did a marvelous job. We passed them gold stars, 2 thumbs up. Before that week was out, they received a non-renewal notice from their insurance carrier for too much wildfire risk. And unsurprisingly, the couple called me up, the supposed fire professional, and asked me how that could happen. And I couldn't explain that to them, which is really what started me down this road myself. And so one of the challenges we have right now is that even if we do the hardening, we don't really have the systems in place to make that fully visible to the risk transfer industries. And there's a lot in that. There's the primary admitted market. There's the surplus lines are not admitted market. There are reinsurers, which is really insurance for insurers for larger, low frequency, high consequence expenses. We have the California Fair Plan, which is a different kind of version. There's a whole supportive industry of modeling. And then there's the actuarial science that sets pricing premiums so that it matches, risk and exposure. So again, we can do a lot of work in the structural hardening space, but we're not being very effective right now in translating the presence or absence of those mitigations to the risk transfer industries. This area is of great concern to me. If we can't figure out how to price climate-induced risk in our systems, we'll have some cascading problems, some significant ones. And then, of course, you can actually do the structural hardening for ignition resistance, as I've discussed. But these are not the same thing. So physically, as you're doing the work or you're helping people do the work or plan the work, be mindful of these three domains of what you're doing it for, what kind of risk you're solving. I think the other one is really important about what stage are you doing this? And really from my perspective, there's three. You can do this kind of work in new construction. So this is really the realm of code sets and, coming out of the ground with a clean slate. But even in these cases, we're doing some work with Rancho Mission Viejo, and they had some challenges. They're coming out of the ground, new construction, comprehensive set of WUI building codes, and they couldn't get their buyers to receive insurance. And so they were sort of stuck. They couldn't advance, even though they were meeting these regulatory compliance issues in the new construction phase. Our institute really focuses on the retroactive hardening portion because the existing inventory of structures is what we have now, and we can't build our way out of this. We're going to have to figure out how to keep these communities from burning now and all the associated consequence with that. So I really focus in that space. But that's different than new construction. Retroactive hardening has a lot of different challenges. They're very unique, but we do have pretty good science on how to go about that, and we have some standard mitigation packages. I like to point to the Insurance Institute for Business and Home Safety. Really two bodies of mitigation packages there. One is the wildfire prepared home, which is really the home and immediate parcel. And then in draft stage right now is the wildfire prepared neighborhood that will look at this more in scale, which is really the place we need to do it. And then the last phase that you could look at this is really what a lot of your discussion is about, I think, right now, following the fires in Altadena and Pacific Palisades, is during the recovery process. And as you know, you've heard this over and over again. I don't mean to be flippant about it. I've just seen so much of this, is that you have the conflagration and you have this recovery spirit, which is very healthy. It's necessary to recover. But it's, we're going to build back, fill in the blank strong. And then the costs associated with bringing new construction up to new code is entirely different than what those prices were previously. We're also finding that during the recovery process, people realize that that their homes were covered from an insurance standpoint for what their original cost was, but that insurance contract is not nearly enough to cover the new cost to do that. And so, again, just to summarize back, through these elements, we lose most of this to embers. It's a very small percentage of the fires. They're low frequency, very high consequence. We have 3 risks that we're looking at. We have, ignition risk, got regulatory risk, and we got financial risk. Solving for one does not necessarily solve the others. In fact, it's frequently not the case. And then how you go about this in terms of temporally, where are you doing it? New construction, retroactive hardening, or in the recovery process. They're all pretty distinctly different. And with that, I will turn it over to our next speaker.
Thank you, Frank. All right, I will share mine. All right. Good afternoon, everyone. My name is Nate, and thanks, Frank, for that introduction. This is the video that Frank was talking about, and you can see lots of greenery still intact, and many of the tall trees are still intact. But you can see this direct relationship of structure to structure conflagration. What are we talking about when we think about a wildfire or even an urban conflagration? What's interesting is when you look at different types, and it's important to note that depending upon the region of the country or the world, for that matter, that you're in, you may get different fundamental fuel types. And for example, a grass fire results in temperatures 400 to 800 Celsius with extreme temperatures of 1,000, but the time period is maybe seconds, which is significant. So it's a high intensity, but very low duration. California has more of a shrub environment, chaparral. Similar temperatures, slightly elevated temperatures that are extreme, but again, longer durations. And Frank had alluded to the Crown Fire, that's got high temperatures that, with the massive fuel burning, you can get temperatures as high as 1,200 degrees for maybe a 90-second duration as it passes over based on the speed. In contrast, structure fires experience even higher temperatures, again, as a function of the density of the fuel. And instead of lasting seconds to minutes, they are minutes to hours. And when you're talking about structure to structure ignition, such as what we see in the wildland urban interface, 10, 11 minutes is sufficient to ignite a structure next to you from radiation. And when you have embers driving that, which is what tends to happen, you have multiple fires. And so you get really a combination of many different factors working together. Very fundamentally, we think about wildfire ignition in terms of the direct contact to a home. That could be from trees, but it could also be from a fence. It could be from your shed. If it's too close to the house, it could be from furniture that was left outside under an eave or next to the house. Embers are one of the main contributors to these fires, of course, and the particularly tricky aspect of embers is that you ignite sometimes thousands of fires simultaneously, and that includes fires on the roofs and around the home. And then radiant heat and flames, that in of itself with the embers causes structure to structure fire spread. Embers, loosely speaking, they say maybe 2/3 or more, between 60 and 90% have been documented, that the embers are documented as the primary cause of structure to structure ignition. Certainly, embers were responsible for what we saw, for example, both in the Palisades and, as shown on the screen, the Eaton fire. We're looking at satellite photography showing simultaneous fires resulting ultimately from that massive exposure to thousands of embers simultaneously. Embers will ignite spot fires, and what's particularly challenging is they may be landing miles ahead of the actual fire front. So you can look through the binoculars at the fire, and you can start to be affected by embers a long distance away. And then, as Frank had noted, they accumulate on the building. We call them stagnation points. It could be directly on the roof. It could be at the base of the structure. And that is why embers are particularly dangerous in a wildfire event when you combine it with combustible elements. It's simply lighting a match to what's a combustible fuel. Direct flame impingement occurs especially when you have wind combined with large fires. So your structure fire that we know can last for minutes and hours, when you have winds like what we saw, between 50 and 100 miles per hour, that causes a significant tilting of the plume. Engineers have studied plume tilts. This was done in relation first to jet fuel fires and jet fires, where they would test and burn entire jets and do large pool fires. And they were able to come up with correlations to know exactly how flames tilt. But the point being, when you're proximate within 40, 50 feet of another structure during high winds, you might actually experience a flame tilt that would cause direct flame impingement. And so the exposed elements of the building, rafters, combustible siding, soffits, decks, they all become this point where you have a direct piloted ignition. So what can we do? Well, we try to remove the fuel from the zone around the home, and we can use ignition resistant or non-combustible construction to try to minimize those impacts. And distance is probably the best thing we can do, but it's also one of the things that our zoning codes have really, we're trying to densify at the same time. But what we're trying to do that's different from what has been done successfully to avoid conflagration is we're densifying with very significant amounts of combustible construction. And this is exactly how many of our cities have had these conflagrations in the past, not because of wildfire. Wildfire is just like the match that lights the fire in this case. But this is what happens is your structure to structure contributes to massive and quick fire spread. Radiation is significant, of course. When you see a large structure fire somewhere in the city, you'll often see that the fire departments will set up these hose streams between buildings to guard one building from the next. This is why, for example, type 3 construction was developed, which is non-combustible exteriors. It used to be type 3 was primarily brick, and over time we changed that to limited combustible construction. So we allow fire retardant treated wood on the exterior walls, but it's to help resist the effects of both impingement and radiation. Again, as a mitigation, we think about non-combustible siding, separation between structures, and elimination of near-home combustible. Just a reminder, to see things we take for granted are the very things that contribute to wildfire spread. So when we look at the numbers as it relates to resilience, there are many studies out there. In one particular study of it was actually over 41,000 homes that had burned in multiple fires, there were some key conclusions that were reached. Number one, homes with enclosed eaves and mesh, 1/16 to 1/8. Smaller is better, though there may be impacts on flow rates. They had a 2 to 3 times high survival rate. And having enclosed eaves yielded lower risk of destruction, 21%. Open eave homes with unprotected vents had ignition rates that exceeded 70%. And in some fire perimeters, That eave condition was more predictive of survival than even the roofing material. And the roofing material, for example, had a 12% lower risk of destruction statewide. In Bay Area screened vents, vent homes were 24% less likely to burn compared with homes that had unscreened vents. And again, what it shows us, and Frank had said less is attributable to radiation, it shows us that exterior siding and even roof material, though we shouldn't underestimate the importance of Class A roofs, they're a little less important than you might even think based upon the actual data. So I'll start with, what do we do? Passive fire protection. You can't talk about passive without thinking about what you do with the space around your home. And there are different names for the zones, but we all refer to essentially 3 zones. One is the immediate zone, which is the first 5 feet within the structure, next to the structure. That's super important because of the potential for ignition due to direct flame contact. This is how houses become engulfed. They ignite because something that's smaller ignites and then ignites the structure itself. The intermediate zone is from 5 to 30 feet. And the idea is to limit the total fuel load in this zone. So this sometimes contradicts what we see in many of these neighborhoods, which have significant combustible zone loads. And then from 30 to 100 feet, we try to space mature trees, and essentially, again, it's another low density zone. Dr. Jack Cohen, who retired from the United States Forest Service, his comment really hit the nail on the head. We don't have a forest fire problem, we have a home ignition problem. As soon as you come to that realization, it changes your view on wildfire.
So from start to finish, we're going to start with our ember generators, which we use to recreate a realistic ember exposure. Embers are those small burning and smoldering particles that may travel ahead of the fire front. And what we do with our generators is we create the realistic exposure, and in our wind tunnel, we're able to throw them at a building. And then we have a building that has 2 sides to it, a good side, which uses wildfire resistant construction, and what we're considering a typical building that we would see in a wildfire prone area. Exactly as we expected, that mulch on the ground there caught fire from the embers. The fire from the mulch burned up under this deck, and this whole deck was on fire. And so this fire on this deck caused flames right against the home. And then if we look there at the base of the door, there was actually the flames from this deck that burned through the bottom of the door, and on the inside of the house we started to see smoke and flames. And so because this deck was a combustible material attached to the building, when the embers led to the ignition of this deck, we got flames inside of the building. Here we are on the wildfire resistant side of the house, where we had non-combustible siding, a 5-foot non-combustible zone and 6-inch gap. We had a metal gutter and multi-pane windows, and we see in comparison to the non-wildfire resistant side, this side had the same ember exposure. If you look here in the mulch, you can actually see some of the embers that had accumulated, but because they had no susceptible fuel to ignite, they just landed there and fizzled out. Now here where we have ornamental vegetation, that again is susceptible to the embers, but because it's more than 5 feet away from the home, it didn't have enough energy to ignite, and it never led to a flame impact on the building.
Again, that's from IVHS, which is one of the premier research institutes for wildfire. In terms of passive resiliency, we think about Class A roofs, asphalt, tile, metal, composite. These are roofs that have been tested generally, and they are tested, in terms of their flame spread, but also their ability to resist burn through. And That's essential for many reasons when you're talking about embers landing on a structure and sometimes accumulating where you have variations in the roof slope or different parts of the roof meeting. Non-combustible siding is another thing you can use, but we're not limited to non-combustible siding. When non-combustible siding is important, especially is when you have a significant radiation hazard or spacing that's inadequate that could lead to flame impingement. Flame-resistant windows, dual pane tempered. UL has recently conducted some really great tests that show the significant benefit of dual pane tempered versus single tempered with a second non-tempered or non-tempered windows. And enclosed soffits, eaves, ignition resistant decks. Again, when we think about eave design and vent performance, the size of the openings is significant and it's very important. At a minimum, you want to do 1/8 inch to get your best performance to prevent those embers from going through. And some folks use multiple layers to catch the eaves. It's a lot like when you have a chimney. Oftentimes we would have an ember guard on a chimney to prevent the embers from coming out. It's the same concept. When an ember hits a metal vent, that metal is thermally thin. It transfers the heat away quickly, which can cause it'll cause the ember to stop combusting because it cools it rapidly in that process. It loses heat to the vent. In the campfire, homes that were built after the WUI code showed a higher survival rate, 44 versus 37% for homes built just after the fire, and only 11.5% survival for homes built prior to 1997. So as Frank had mentioned, the codes are not sufficient if you want to, it's not even 50% if you just follow codes, when you're constructing, designing, and maintaining your home. It's part of the story and it will get you partway there, but not all the way. Other things, metal gutters, debris guards, ember resistant vents are very important. Drip edge flashing, limited, and we want to limit entrant corners and roof valleys. Now I'll talk a little bit about active fire protection. We often think of building sprinklers, and in the context of home protection, we also think about exterior systems. So roof sprinklers protect from above, wet roofing, soffits, vents, and upper siding. There have been many case studies that show high survival rates that are above the norm, some approaching 90 to 100%. Perimeter sprinklers are around the property. They wet the vegetation and the base of the structure, which is where the embers, of course, accumulate. And it's you want to have wind-resistant spray heads and backup power. So here's an example of a system that you could utilize. This is a system that includes sensing devices that understands when the fire is approaching. It can be activated sometimes manually or automatically. They are developing, and there are many of these systems out there, but this one includes a number of facets that I find are very important. A foam, which has greater, basically its surface tension is higher, so it sticks to the fuels longer and it retains water better. A tank and a pump. What are we going to lose in a fire? We're going to lose water. And we know this. When you have hundreds of fires, we can only push so much water through our pipes. So you're best advised to provide some kind of secondary water, whether it's a pool, a tank, or otherwise. And controllers. These are not activated solely by heat. You need to activate them before the fire can be sensed through heat, because embers don't produce significant heat until they cause the structure to burn. Exterior sprinklers pre-wet zones, interior sprinklers suppress the interior fires. if something should get in, and they do get in, they break through windows all the time. And again, this is complementary to passive resilience, but not a replacement. There are other elements that we've seen and utilized, deployable barriers and fire gels. So fire gels essentially hold the water in and cling to surfaces. So wet fuels do not burn. This is why many parts of the country with higher relative humidity and moisture content don't experience significant wildfire. Deployable shields can be used where you are close to a neighboring structure, or a significant fire exposure. And these are, of course, best used just prior to the wildfire, because every hour that you leave these out, they're prone to evaporate, the water comes out, and you're back to square one. Here's an example of treated and untreated grass using a fire gel. And this is pretty dry stuff. So you can see that it's a very effective way to limit the effects of fire. And the last tier is facilitated fire suppression. This is what I say when the fire department pulls up, they have to make a choice. Are they going to try to save your structure or another structure? And if you give them the right tools, they can help save your structure. So why not get a portable fire pump, have it available with a hose to wet down spots? It's difficult to carry water into fires, especially wildfires. So if you have a pool, you can draft from the pool, you can draft from a tank, and that is something you can use to have the grounds wetted if you don't happen to have a fire gel. You can even hook up an educator and basically add materials that make it like a foam, and there are biodegradable foams that do not harm the environment. Monitors and nozzle systems are for very large properties. Again, you can integrate it with foam or gel adductors, which are mixing the two materials so that as it comes out, it's in solution and will adhere to the plant material and to the structures. And they tend to place these on ridge lines, fence lines, property corners, and whatnot. So this is a way for you to fight back, in your own neighborhood, and protect possibly people around you, because you actually form a defensible space zone when it's got a high moisture content that can then be used to extend from and protect other areas. So I have this picture here, which shows homes everywhere burned down, but these pools are full. So it would seem that there's a benefit to being able to use that water to wet down the structures during an event. If you have a 30 or 40,000 gallon pool, why not use it, as you know this fire is approaching? But be aware that these systems have complexity. You need to make sure you have adequate generators or backup power. In some cases, you can have a very simple kind of backup power, like a 12-volt battery, but other cases you may need something more sophisticated. And you look for a continuous capacity, for up to 8 hours in many cases. So I'll leave it with this notion that we need to think about layering defense. I think about it in 3 tiers. Passive first, which will get you about 70% of the way there, or maybe 50 to 70, and then you add in active, and then let's help out our fire departments. It's incredibly difficult to fight thousands of fires all at once, and we need to do everything we can as a community to create ways to help fight these conflagrations if we're not going to change our materials. And we can build with combustible, non-combustible materials. We just have to think about the exposure to which that material will be exposed to. So, and maintenance is important. We have to think about maintenance because things change over time. So thank you very much, and I will pass it on.
Thanks, Nate. I just want to check, make sure my screen's visible there.
I see
Great.
it.
Yeah, so picking up from Frank and Nate, extending further on wildfire resistant construction, share some of our collective lessons learned with RDH, looking at various other fires throughout North America, and then looking at some of the rebuilding assemblies and details that we can use to focus on that passive hardening approach. Standard disclaimer, so outline, we'll look at some case studies, let you know how your project may be at risk or is it at risk, look at wildfire resistant construction details and assemblies, look at what this may cost compared to non-wildfire resistant construction, and then share some resources that we kind of mentioned throughout this presentation, and then we'll finish with discussion and questions. So start with some case studies. I just want to take a moment and say that, these fires are, impacting our communities and devastating in many ways. But I think as a AEC community, we have a vital role to rebuild and help our communities to be more resilient and resistant to these devastation moving forward. So looking at Lahaina, so we mentioned wildland urban interface, top right picture shows that. And we mentioned conflagration. So that's essentially what Maui was started with wildfire, and it quickly became a structure fire situation, where there are a lot of, wood and shake roofs, single pane windows, things that we know are not resistant to wildfires. So we can see that this is a problem that's going to persist, and they have a report saying that more and more wildfires will happen like this in Maui moving forward. And then we touched on the campfire case study a little bit with Nate and Frank. So similar statistics there, and then one kind of another depth and layer to what was already been mentioned. So there, obviously we saw with the WUI codes going into place in 2008, there were some better results, but it's largely an existing building problem, and there are some guidances out there. You can see 2008, there's a voluntary defensible space checklist thing that homeowners could use to help harden their homes. So it's just something that the codes can only go so far. At that point, it becomes voluntary, and there are costs involved, but the payback on this can be pretty drastic. So just even though we had some wildfire resistant construction, this is kind of the results we can see. And then mention there's some photos that we took from another fire in Canada, in Jasper, Alberta. So just looking at different assemblies and how they fare during wildfire, we can see top left eaves in exterior insulated finish system. On the left, you can see some combustible siding, but below that was a gypsum wallboard. Stucco on the right, everything else is burned beside that stucco. So we do know that is a good assembly and good material to work with. And then bottom right, you can see some vinyl siding and Kynar coated aluminum in the soffit there. So roofing assemblies, cedar shakes, highly susceptible to wildfire. Our asphalt shingles on the left there are certain ones that are better than others. But as we mentioned, the materials are important, being Class A. And then we had mentioned various fuel sources around that defensible space, and really taking a look at existing properties and buildings. And these, you can see fencing here that's caught on fire and added a lot of drastic fuel to the fires there, resulting in loss of structure. And then we talked about embers and how all these fires start. A large component is the embers and the ember blowing in the high wind conditions. So as simple as what Nate had mentioned with a certain size of mesh, even, bottom right here, this is looking at an intake, vented attic louver. But behind that, you can kind of see, if you look really closely, the mesh in there help that structure to survive. And then on the left side, what you might see in a lot of homes with the soffit venting, the Kynar coated aluminum. So Nate had mentioned, multiple layers of protection. We may have this, but behind that, we should be looking at a mesh potentially to provide that true fire resistant performance. And then window assemblies. So it's, a huge vulnerability in homes. Once the windows break, it's a direct path for embers and fire to get in. So we had mentioned tempered versus non-tempered glass, and can't stress the importance of that. So at minimum, single pane on the outside portion of the IGU, 2-pane IGU, but better yet, 2 panes from recent testing that we know of. And then the frame material, you can see on the left here, we have vinyl frame windows. And the photo above is that IGU just falling out of that unreinforced vinyl frame window. So, if we are looking at vinyl, it should be UPVC and should have internal reinforcement in the form of steel or metal channels to hold that IGU in place. And then top right is actually a metal clad wood windows. And I think, the fire broke through and caught the wood on fire from the inside of that assembly. But, using a frame material that is resistant to fire is important. And then you can see the glass breaking there, whether it be from heat or, high winds, missile or debris contacting windows. Concrete foundations. So it's, I think we're kind of at that point where everyone's trying to assess if their concrete foundations are sound after, the fire and can be reused. So, we think about fuels adjacent to foundations. Say if there was some insulation against foundations, that's a good fuel source, similar, wood chips we saw in that one video. So it's, different fuel types that can contribute to the foundations being damaged and potential for reuse. And then, one that's less mentioned, metal buildings, all metal buildings. So you can see, high heat has pretty drastic impacts on those buildings in that case. And then finally, Nate finished on sprinklers and active fire protection. So you can see some examples here, of more makeshift or, various, homeowner put together suppression systems. You can see the tank on the bottom right with a pump and, more of a durable hose. You can see bottom left, just a common sprinkler with a garden hose. Just want to be careful with that, that can resist high heat intensity and do its job throughout the fire. So kind of looking from lessons learned and case study taken away from that, not every building is susceptible or should be designed for wildfire resistant construction. So I think it's a good first question when you're thinking about rebuilding or building in or adjacent a wildfire prone area. And we have building codes, obviously California Building Code and in Chapter 7A. There's also the International Wildland Urban Interface Code, which is a model and provides some good information as well. And within those codes, they define which areas are wildland urban interface zones. So this is the CAL FIRE map online that you can type in and search. You can see various severe high wildfire zones. But I think Frank had a good quote. We were talking a few days ago and said, these maps, I don't know exactly when this one was put together, but we obviously have some changes going on in in climate and even locally. It depends on kind of a house to house, neighborhood to neighborhood basis. It may not just be a zip code or this map that, this is what's going to require you to do buoy enforcement by code. But you have to look at your own site and understand what's the risk to your property and where you're building, if it makes sense to go above or beyond the code. So what is wildfire resistant construction? So these kind of two paths that we view and look at. So one on the left using exterior rated gypsum sheathing, and then on the right, another good option is using mineral wool or other fire and heat resistant exterior installations. So serving kind of multiple purposes with material, both energy and sustainability wise, and then also providing fire resistance. But in the code, we define various assemblies and all that, but you have to think about the transitions between all those assemblies and the various vulnerabilities that happen in our building naturally that may not be fully captured or thought of in the code. So the importance of details, we have to start with wildfire resistant 1 hour assemblies, but then looking at the details, so getting in between those assemblies. So focus, non-combustible materials, resistant to high heat temperatures and embers, blocking embers, and then protecting high temperature sensitive materials like liquid and plastics. And then the last piece, I think, thinking of rebuilding and new construction, in the worst case, if things do go wrong, how do those materials contribute to, say, soil contamination and such? There's a lot of volatile chemicals and things in building products. So is there a way that we can use more environmentally sustainable or positive materials that may not, cause such an impact if things do burn, or is it easier to rebuild after that event? Just something to think of. And then ourselves at RDH, we think of the building enclosure about control layers. You're controlling air, you're controlling the thermal and heat, you're controlling water, whether it be rain. So we always like to have a continuous barrier that provides that one control function. So we always think about, like I said, bringing those assemblies together. Can you draw a continuous line through your details showing a wildfire resistant barrier? And it's going between your roof walls, all the trim vents, what function or what material is serving that function to resist wildfire. So just go to some examples. So these are some guides we put together for various agencies throughout North America, and partnered with Rockwell recently for like a guide as well. And this is just pulling and reminding us what is in the code and what is required. This is from the Rockwell guide for California specifically. So looking at common requirements, there's within the code, there's various options to get us to code compliance, being covering the assemblies, having that 1 hour fire resistant rating, or using gypsum, like I mentioned before. So looking at roof coverings, Class A is always a good place to start. Looking at bird stops and various venting requirements as well. Looking at the walking surface, defensible space around, and what provides some fuel to the fire in the worst case. Gutters and downspouts. So Nate had mentioned, not allowing things to accumulate using screens and such. Exterior walls, looking at those details at the base of wall, various transitions. And then looking at, say we have a ventilated crawl space, how do we prevent embers from getting in there? And similarly, appendages and projections, being non wildfire resistant, and just think of overhangs without venting or rafter ends. Glazing requirements, we touched on multi-pane tempered is a not good option. And then exterior doors, a lot of tests and things to comply with, similarly tempered glass and thinking about transitions and weather stripping. And then finally vents, Nate had touched on 1/8 inch mesh is a good option or less. So these are some details just pulled from some of these guides. Um, Thinking about various transitions and trims, some good examples of Class A roof and gutters, aluminum gutters, then to the eaves with multiple lines of mesh and defense, and then trim boards and things that are non-combustible at transitions, protecting our framing members with frame construction. And in this case, showing mineral wool is a good option to provide energy efficiency and fire resistance. You can see base of wall, you may, if you need insulation or want to have insulation there, thinking about instead of using, say, a extruded polystyrene or something that's flammable, use something that's less flammable for a certain depth and protecting anything that is flammable with a cement board or similar. And then looking at windows, beyond having our multi-pane and fire resistant frame materials, similar, looking at how our trims are installed and protecting from ember accumulation. You can see some mesh screens in a rain screen assembly. So we need to prevent, embers from going into that great rain screen we may be required to use in certain areas. And then, looking at some deployable options. So integrating fire shutters into, say we do want to have those beautiful wood framed windows, but we are in a WUI zone. So looking at deployable fire shutters is an option to still have that beautiful look, but still be wildfire resistant. And then looking at doors. So you think of doors, we had that example that Nate played with the little deck catching on fire and going in, through the weather stripping. So just small details, thinking of that gap between the frame and the door itself as being a place that embers can accumulate, and even weather strippings within that gap that are usually highly flammable. So do we have doors that conceal that weather stripping or otherwise stop embers from getting into the small little gaps and cracks? And then, taking all these lessons learned and everything, ourselves in RDH, we've done some internal testing and, to show, do these measures actually work and what's the relative performance of each. So you can see 3 examples we have here of the gypsum sheathing with a combustible siding even. On the left, in the middle, we have a fiber cement siding, so non-combustible Class A with mineral wool fiber. And then finally on the right, we have unprotected with wood siding. So kind of the worst case scenario in terms of wildfire resistant construction. And actually, going out and building these, setting them on fire and seeing, what works and what doesn't. And you can see the fuel cell down there is, it's not just a stack of sticks. It's, designed to have a certain fuel density that you would see based on, wildfire, past experiences from Australia. They have a pretty thorough wildfire fuel intensity rating. And you can see the result here of the unprotected assembly with wood siding. So we did have a roof up there at the start, so that's now burned off, and so shows the true consequence of some of these unprotected assemblies. The middle one with the gypsum sheathing and still a combustible vinyl siding. So you can see on the left that siding has fully melted off, and you can see below the gypsum is what we have peeled away here after the test. So even though the siding's gone, gypsum's charred on the exterior, you peel that gypsum away and our structure is perfectly fine and serviceable after these fires. And thinking about the structure to structure spread, thinking about setbacks in architecture and something similar we may require with gypsum. So this is serving that purpose of preventing structure to structure fire as well. And then finally, what I think is kind of the gold standard being the fiber cement or non-combustible siding with a secondary layer being mineral wool, providing multiple purposes for a single material. So you can see the fuel cell in the bottom left there has self-extinguished or put itself out with fiber cement, a little bit more brittle, cracked, some smoke staining and other things. We peel that back and you can see that the fire did get behind that rain screen, or the heat did get behind that rain screen and charred a little bit of the surface of that mineral wool. But beneath that, we peeled that further, and the WRB and sheathing are just fine. So coming in from case studies, lessons learned, assemblies that we use, looking at the cost analysis. So there's been various cost analysis for this wildfire resistant construction. We've done our own internal little cost analysis and looked at others. So actually went out and got quotes and did full QTOs, everything for unprotected versus wildfire resistant construction. So you may look at a typical house, asphalt shingles, common things on this list here, and then look at a wildfire resistant house. And really, at the end of the day, looking at what's the difference between wildfire resistant and non-wildfire resistant construction. It's all in the minor details, and a few things may add more cost than others. Say your gypsum sheathing or adding mineral wool. Some minor things, screens. Another thing that may add more cost is the tempered glass within windows or non-combustible frames. But the others, a lot are kind of baked in or already something that we may use. So preliminary results and from other studies on this, like I mentioned, things that a lot of things don't change. We don't really use vinyl gutters, downspouts, asphalt shingles that are usually Class A are used already. Mentioned the tempered glass adds a little bit of cost, but overall, above base code or code design for providing wildfire resistance, maybe up to 2% cost increase from that base code. But I think, as architects, rebuilding for clients, kind of have to reframe that 2% up front. It's, there's always a budget and always construction costs, but thinking of down the road, the payback for that mitigation can be significant. And, it's a quote, I think from AIA, the $4 to every $1 spent on mitigation being the payback. So I'll finish with some additional resources, some that we touched on throughout the presentation, and then just others that are good for architects, contractors, engineers to reference. And there's a lot of research that's gone into this subject, and I think these are a good baseline of things you can look into while you're thinking about redesigning. And that's all we had for you today. So we're going to finish with discussion and questions.
Thank you so much, everyone. I'll jump in here briefly along with, I'm Greg Kochanowski, the co-chair of the AIALA Wildfire Task Force, as well as Mohammed Sharif, who's also on the call. So we'll be fielding the questions for you in the Q&A. So Barbara, I think you had your hand raised first, Barbara Leon.
Hi, good afternoon, everyone. I actually think my question was answered. I wasn't familiar with the wildfire resistance barrier. That just means a gypsum board or whatever layer that is. It wasn't the same as the water resistant barrier. So thank you.
Okay.
Yeah, that was more just transferring, thinking of, say, the water resistant barrier having to be continuous. It's thinking of wildfire as the same or another
way.
barrier that has to be continuous. And can you draw that line through your details and assemblies? And
that's a great way to think about it. Thank you for that clarification.
Yeah.
Aaron? Sylvia?
Okay, and I'm gonna try and start the video here. I have lousy lighting in here. This is not for me. I'm in my kitchen and I was thinking about silicone. We have these silicone things that are fire resistant anymore. And I did a quick search, silicone fire resistant sealant. We're not seeing, I don't think, but silicone based exterior materials, but just to demo it, silicone's really flimsy, as you're aware, it's very flexible. But this particular device has, I think this is plastic because I've got burn marks in it, but there's plastic inserted within silicone here and it is not flexible because it's getting rigid from the interior material and exterior is like fire resistant. Long story short, do we see any exterior surfacing materials, for example, like a replacement for vinyl siding, that kind of thing, that are made of silicone? Because I'm not seeing any, and it seems like that's possibly a resource aside from cement fiber and all that metal and stuff. Question.
Yeah, I'm not aware of any true silicone based exterior products or largely composed of silicone. I think, you mentioned the flexibility and that may not fare as well as exterior cladding in that case, but maybe there are some out there.
The only other thing I've seen, not silicone based, I think the company is called Arklin. Maybe they're doing a chemically bonded layer of intumescence. It's pretty compact, pretty efficient, but it's intended to be painted over as well. But nothing silicone. But there are new materials being looked at for this type of resistance.
Okay, good. I just wanted to toss that into the idea bank. Thank you.
Great. Kelly?
Hi, thank you for your presentation. Had any resources you could share with us specifically for historic retrofit? A very specific question is I've got a homeowner with a home from 1912 with single pane wood windows, and they're trying to decide if replacing the historic glass with tempered glass would make a difference. And is there any type of guide that would help us weigh our options? Is that worth the investment in changing the glass, or would those single glazed windows be lost anyway?
Yeah, I think you say single pane untempered.
Untempered, yeah, they're original.
Yeah. So yeah, unfortunately, we do have testing and understanding that untempered single pane is highly susceptible to wildfire. So if you are looking at making that historic building wildfire resistant, there are probably a litany of measures you could take, but looking at tempered glass and maybe other shutters or otherwise that could be installed just before a fire, maybe an option.
Yeah, and you also want to think about you can't just substitute an inherently resistant material like tempered glass with something that tends to shatter and break and fall out, which is what regular glass does. And that's one of the key problems that you face with regular glass. It's very, very sensitive to temperature differentials. So if you have an exterior sprinkler system, but it's spraying and it was hot on the glass, that could cause that glass to fail. And then that becomes an intrusion point for embers and whatnot.
Just to add one last item on that, even with replacing the glass, a structure of that age, you just need the weakest link to lose the rest of the building. So the expense to do the glass, you may find an answer, only to find out that you've really only solved maybe 5% of the exposure problem. So really have them try to think at it holistically.
And I think there's an issue also with the wood sash, because if they're wood frame,
Yeah, it would.
you may need to be coated with something like intumescent paint and then buy so many layers of it just to do it, and then other modifications to the window sash in order to accommodate a thicker IGU that would come from a tempered glass setup of double panes.
I'm glad you brought that up, Richard. The intumescent paint and swapping out the tempered glass are the two things that we are looking into. But just wondering what kind of impact that would make in our project.
Not sure if Richard, you were about to answer that or someone
Well, I
else.
just don't know exactly what that would
Yeah.
pencil out, and so that will have to be a little something to be pencil out what that kind of cost would be, and see what it is and if it works. Or you
They're
might find
related. I'm sorry, Richard, please go ahead.
or you might find an option that a new window that can be made that follows the design pattern of the original to replace the old and then preserve that old window somewhere.
Along those same lines, there's a question here about the use of laminated glass in lieu of like a tempered IGU. Any thoughts on that from the panel?
Yeah, I have been looking into that, but you have to make sure that under the intense heat, you've seen what the post-fire conditions look like. So under the intense heat, you would have to ensure that the laminates can withstand that heat and not lose their adhesive qualities. Otherwise, you're back to square one. That being said, laminated glass is probably better because, again, if that outer layer breaks, that laminate will hold that layer in place longer. But it's a real question as to the true heat exposure that it faces. And that's why, again, tempered glass can stay in place even though it spiders, it will stay in place longer typically, and it takes much, much higher temperatures to cause that spidering.
Yeah, it definitely has to be the right laminate. Yeah, I've had a picture of, think of your car windshield that's laminated glass, and after a fire, those fully melt. So it's all about the right laminate as well.
Great.
We have a couple of more
we do have
raised hands, right? Right?
Yeah, go for it. Yeah, Craig, please.
Thanks. I was wondering about that wall assembly that had the rock wool and then some looked like 1x4 wooden battens and then the cladding attached to the battens. And it looked like the flames got up into that ventilation space under the cladding and started burning the wood battens. I was wondering if there are any other materials that would be better to use for those wood battens that are less flammable than wood.
Yeah, I'd say that I don't know if they burned them. I guess it was maybe the vinyl situation that maybe burned them more. In the fiber cement and mineral case, those were fire treated battens, and I think it was more soot and surface charring or whatnot. So using fire resistant battens, and even if those do catch on fire, we still have the full mineral wool behind that to resist. So they should be fire resistant, but there are other materials that could look that are fully fire resistant.
I was wondering, like, do you have any suggestions of what one might use there instead? Because I guess PVC would have the same problem as the siding itself, and then maybe metal wouldn't hold a screw. So I'm not sure what would use.
I think fire treating wood is still the best option.
Okay, thanks.
I think Daniela was next.
Hi, thank you. I just have a question regarding if you had put together an assembly using a zip system, Cameron. Have you worked with it?
Yeah, in terms of building enclosure, yeah, I'd have to double check if that's fire rated sheathing.
Yeah, because it has the the value of giving you insulation plus sheathing for structural shear wall.
Right. Yeah. No, that's a good question. I think you could easily check fire rating on that material to see if it complies with code.
So you may need to add Gboard, right, or the wall.
Possibly, yeah.
Miriam, you had a question? Maybe not. So there's another question that just jumped in from Pooja. For the amount of heat exposure as we saw in the recent wildfires, what is the balanced approach between construction detailing and cost to create structural hardening versus for structural survivability? If you caught all that.
Yeah,
Sorry,
Maybe Pooja,
I
you just
missed
want to
that.
jump in here?
Yeah, I do. Thank you, Greg. So that's a basic question, but we also saw new construction with Class A fire rated construction burn during the fires. And so I know there are individual testing that has happened, and we're going to do mass construction, assuming we're going to do mass construction at some point. If there was another event like this, do we know, or has there been testing that shows that if we were doing all of these things, that we're going to be able to get structure survivability?
Well, I'll take a stab at it. First of all, there have been studies by organizations like Headwater Economics that have looked at wildfire resistant construction versus non. And some of those studies have shown comparable costs. In fact, one showed a cost that was slightly less. So it's really about material selection. And part of this is what's the aesthetic. It can vary widely, as you know. The real issue is very often we skip out on details. There are countless details in the construction of a home, for example, where you have this opportunity for, embers to penetrate, or you forget and use a material that's highly combustible where your neighbor's property is not protected. You don't have proper heat shielding. So those things can certainly sometimes add cost. But as far as the effectiveness, there are also studies that show you can achieve a 40% reduction in loss from structural hardening. And when you combine that, from vegetative hardening, when you combine that with structural hardening, you get up to 70% reduction in loss. The reason why you never have 100%, which you can get closer to 90 with active systems, the reason why you never have 100% is because there's imperfections. It's like every building we've ever built. These imperfections are the things that bring the houses down, because when you're under a constant assault by heat or embers, they will find those imperfections. And Cameron's slides really showed the complexity of some of these details. And I love your way of thinking about it, Cameron, where you're drawing the line, right? That line is often broken. And so it's not an extra cost, but it's an extra amount of care. And so part of it is, how well are you observing the final condition? So I think that's a cost, is make sure that what you expect is being built is actually built, because it is critical and it has to last. It has to have a durable characteristic to it. So.
And if I could also add in there, when you're thinking about cost, and I like the way you worded it in terms of, structural survivability, that, solving for that risk, is the cost worth the survivability of the structure? Honestly, we're too soon. And I mean, we do have good data on the incidents that we've had, but we don't have the decades and decades of experience, because really most of our losses, California's at the top 20 most destructive fires, they've all occurred since 2017. And so we're still ground truthing efficacy on that side, but there's pretty good science to give us reason to go that way. What I would say is also look at what the costs are in terms of related costs, and I'm going to go right to insurability and home value over the long haul. We have situations where property values, I think it was National Association of Realtors, not terrible, but I think something like 4.5% reduced value if you're in some kind of an elevated wildfire zone nationally on an average, much higher in other places. But when you start adding challenges for insurability, period, if you can get it, cost to go to a fair plan, those types of things, those are also cost avoidance and should probably be, we're going to start looking at pricing in risk. And so I think it brings some added value there.
Thank you.
There's a series of questions here in the chat about metal versus wood framing. I'm not sure if any of you have it seems off the top that metal's better than wood, but has there been any testing with regard to that any of you have participated in or know about that could maybe address some of that conversation?
I won't go to, I'll let some of the other materials experts discuss that side. But what I would say is that certainly the metal wouldn't burn where the wood portions will. But by the time we're down to that level of exposure under these high wind conditions, we've already essentially lost the building.
Yeah.
And so I don't want to put too much stock in that. I think, again, the key is keeping the embers from being received by the structure and allowed to incubate with a lot of oxygen and a lot of other collection in the same spots, because that's how we'll start this exothermic runaway. So by the time you've got the structural members contributing, we've lost the building.
One thing I'd add to that, just as a thought, and kind of a question, in terms of post fire cleanup and health, public health in the metal stud wood world, what material is more toxic or leaves behind the contaminant?
Yeah, the map.
Yeah, that's interesting. Well, metal doesn't burn, but metal has a higher carbon footprint. Wood will burn, but it has maybe a lower carbon footprint, right? So it's kind of a trade-off. And then there's the question of, if something does combust and you have to replace it, what's the cost of a rebuild as well? And it's a complicated question, but I think often with conventional commercial construction, which is where you would see metal used, those structures, those are the kind of structures that we worry about in terms of what they're producing, in a fire from a post-fire toxicity standpoint. And that's another consideration. So,
Right. That's what I meant. Okay.
yeah.
And I think it comes back to also construction type, but when we're going metal studs, it's more non-combustible construction, whereas we're talking about wood frame construction, which, I would hazard a guess to say that most homes thinking about rebuilding would be in that wood frame construction realm. So it's we get back to the studs with the fire, then, we've already lost the structure, like Frank has lost.
Real quick to your question on the, on the recovery side, a lot of the cost on the recovery is simply, it's the material removal of the material itself hauling away. It comes down to a function of weight. And so oddly enough, we may lose a lot of the weight by process of combustion, but the cleanup costs can be remarkably different depending on how soon it rains after the incident. So just a ton of variables on that side.
I want to, Ian, you had a question in the chat, but weren't able to raise your hand. I don't know if you want to jump in here.
Okay, my question, can you guys hear me?
Yes.
Okay.
Yes.
So my comment was, particularly in certain jurisdictions, their zoning codes are difficult and they're requiring things that are contrary to some of these better practices, like requiring high amounts of landscaping fuel next to the buildings, wood materials on the building spanning things like cement, board sidings. How can we convince these certain jurisdictions to change their zoning codes, including I just looked at a map for my project. It's now in the new high fire hazard zone.
Yeah.
And they're saying, no, you have to use real wood siding.
That is a great question, Ian. One thing to remember, I said it a couple times, I'll borrow an example from COVID. One of my favorite epidemiologists, never had one before COVID, but Dr. Michael Osterholm out of Minnesota, and he worded it great. He said, the reason it was so difficult, normally when you do the science, you get to do the science off in the lab and then bring it to the application. But in COVID, we were doing the science in real time. Full disclosure, loss of all elegance in the process. And that's what we're doing here. We're in a transition, again, thinking of 2017 as kind of our pinch point for the state. We're in the middle of all of this. And so the idea that there is an elegant first step, a playbook that's established, we're just not there. The number of existing conflicting policies from a regulatory risk standpoint. Remember, I mentioned earlier, you can be solving for one and bump right into another one. Structure density. We need to densify for housing shortage, and yet we're saying the density is one of the top fuels. Or an excellent reference to Dr. Goldner's work in the chat on that. So to me, the first place we'll get this is we have to get local governments to understand there's an expense for not adapting. And right now there's a little bit of in my opinion, a moral hazard there because they're sort of insulated from it. I think once local government, specifically by way of property tax reduction, by devaluation, there's a lot of mixing in the price signals right now, but I'm really watching the general obligation municipal bond market. If it turns out that it starts to be an expense not to adapt, and there's a cost to not doing something, then I think we'll start having the kinds of questions, Ian, the kinds of discussions, Ian, that you would need to point out these conflicts and figure out how do we reconcile them. I just don't think we're there yet. I wish I had a better answer, but it's going to be a little while.
And I think maybe, Richard, you have your hands up. Maybe this would be the last question as we approach 1:30 here. So, Richard.
A little less of a question, but I would definitely say it's when it comes to the metal stuff and thing, while it is technically non-combustible when you think of it in the same kind of sense as wood, but it does have ability to melt or structurally lose its rigidity and starts to lose structural strength. Hence why some of the photos you saw, like one of the photos of a metal structure that was all warped up because of the melting, because that's the effects of the metal sagging and whatnot due to the heat reaching a certain level.
One last thing I would add there too, the heat conductivity of wood is very low. I mean, it changes with the direction of the grain, but one of the things that a metal does induce into the system is there becomes a route now for more effective heat transfer by conduction. Not saying that you shouldn't do it, but it's a different wrinkle in that part of the structure.
Yeah. But to echo, I think Frank's point about, once the structure gets to that point where you're compromising your outer barrier and you're achieving temperatures of say 550 is kind of a general, that's not the true temperature, but that's when you start to see the loss of strength and stiffness in steel. You've already lost the game. You got to fight it on the perimeter, on the enclosure itself and beyond the enclosure.
Well, I think that's time. We just wanted to thank everybody for joining and for the excellent panel. One of the reasons we do this is to bring all this education to the AIA community. And as Mohammed and I talked very time, not just put words in your mouth, Mohammed, but like we learn every time we go into these things. It's incredible information sessions. So thank you all for taking your time out of your day. This is many people have been asking in the chat, will this be made available? Yes, all recordings of these sessions are being made available on the AIA California website. This will be uploaded shortly, and then they'll be viewable on YouTube. So you can also search through YouTube if you wanted to go through it that way. I think that's all we have, Mohammed. If you had any, sorry.
No. Thank you so much, Cameron, Frank, and Nate. Ditto what Greg said, and to the audience and the participation. We're learning, and thank you.
Thank you. Appreciate it.
everyone.
My pleasure. Take care.
Bye.
Thank you. And you're invited on April 9th. That's session number 3. Look forward to seeing you.
Yep, me too.
Thank you.